Okay, hello everybody. I know it's kind of noisy here, but I apologize for that. That's where I live. Yeah, maybe you don't even hear the noise, I don't know. But let's talk about this final exam. So what I want to do is I want to cover an example actually from a different course of mine, but it's one of my favorite examples. And what I'm going to do in this is going to be a two video series. The first one will show you about calculating the odds ratios, and then the second one will go into the chi-square. So let's start with the odds ratios here. This is your typical cross tabulation, which is basically a matrix. This is a 1, 2, 3, 4 by 1, 2, 3, 4, so 4 columns and 4 rows, 4 by 4 matrix. The table itself that we're interested in is this 2 by 2 table, A, B, C, D. When you calculate an odds ratio, you're always going to be calculating it in a 2 by 2, in a cross tabulation in a 2 by 2 sense. Okay, so here are a couple formulas related, several formulas related to the odds ratios. The first is the odds. The odds can be defined as the probability of success divided by the probability of failure. So in this case, we're looking at the impact of exposure on some health conditions. So this could be smoking on lung cancer. And for us, in terms of probability, success is whatever we're interested in finding. So the health condition, say lung cancer, would be our interest here because we're studying the effects of smoking on lung cancer. So success would be having lung cancer, and failure would be not having lung cancer. So the probability of success would basically be the probability of this outcome divided by the probability of this outcome here, no health condition. And we could just say we could just do it in terms of frequencies. And I'm not going to go into why that is in this video, but the denominators would cancel out if we were to divide by the totals. But, excuse me, the probability of success in this case for individuals who expose would be A divided by B. So that would be what you would have for one level. Now, if we're making that's just an odds, right? Those are just the odds. If we were looking also at the odds of having lung cancer among those who are unexposed, it would be C divided by D, because C would be success, again, having the health condition. D would be failure, not having the health condition. An odds ratio is merely the ratio of those odds. Ratio is a quotient, so it's division, right? So you'd be dividing the odds for among those who are exposed to the odds among those who are not exposed. So if you think about it, you'd say, what are the odds of having the health condition among those who are exposed opposed to those who are not exposed, or compared to those who are not exposed? So that's a ratio of odds. And we see it here in the formula for the odds ratio, which says OR. We have the odds for risk factor A, and risk factor A in the table would be exposed divided by the odds for risk factor B, so that's not exposed. So that's what your typical odds ratio is. It's just a ratio of the odds. So in order to determine whether this is actually a significant relation, we can do a couple things. One is to calculate something like a chi-square, which we'll do next, or you can actually just look at the confidence interval. The confidence interval has several components to it, and if you take a look at the formula for the confidence interval, you'll notice that there's an E over here. So this is, and we're raising this E, which is like 2.71, I think, something like that, Euler's number, to whatever this confidence interval formula is. And you notice that there's an ln in front of the odds ratio. So this margin of error, so all confidence intervals are point estimate, whatever it is, like our odds ratio, plus or minus some margin of error. So we're going to say that when we calculate a confidence interval, we're trying to find out if the interval contains the population value, and we give ourselves some kind of a margin of error in which we believe the true population value is located. We do that because statistics are generally about making inferences about the population. We're not as interested in the sample as we are in the population. We're trying to make an inference. We're trying to say something about the population based on the sample. So this confidence interval gives us a margin of error here. And this is, again, not a discussion about confidence intervals, so I'm assuming that you already know what the confidence interval is because we've talked about that before. So the margin of error here is already in the natural log scale. So we're going to use this critical value based on a z distribution. And we know what a z distribution, that's a standard normal distribution. And it's z1 minus alpha divided by 2 because there's a value that's below the mean or the point estimate in this case, and one that's above the point estimate. And so it's centered, right? It's at the center of this confidence interval. And our alpha is whatever our type 1 error rate is. And again, I'm not going to talk too much about that right now because we've already discussed that. But alpha is your probability of a type 1 error. And if we set it at 0.05, we're going to be calculating the 95% confidence interval. You got 0.05 divided by 2 is 0.025. 1 minus that is 0.975. So that just tells us where our critical value is if we have an alpha of 0.05 two-tailed, right? Because it's both ends of this normal distribution. And our standard error for this cross tabulation is just 1 divided by the value that's in here, A, plus 1 divided by B, plus 1 divided by C, plus 1 divided by D. And I'm not going to talk about what the standard error is here because I'm assuming now that you know what it is. Okay, so as you know, that has to do with the sampling distribution of whatever the mean is, or in this case the odds ratio is, and it's standard deviation of that sampling distribution. So but we're not going to get into that now here. And again, ln stands for natural log, so that's a log of the number, but that's has a base of e. And just in case you don't know, that's what a log of a number is. So it's the power to which the base is raised to return that number. And in this case, the base is e. So just some interesting stuff for you here. And just again, in terms of odds ratios, odds ratio of 1 means there's no relation. Of course, that makes sense because then the odds of success for the numerator would be equal to the odds of the success of the denominator. So an odds ratio of 1 means there's really no relation between whatever the exposure and the outcome is. Odds ratio less than 1 somehow would mean that the exposure is protective because there's a decrease in the odds of the outcome for exposure versus not exposure. Odds ratio greater than 1 indicates that exposure is a risk. Also, if the confidence interval includes the value 1, that's how we can determine whether we have a significant relation or not if we're using a confidence interval. Because if that confidence interval, so if we take 100 such samples and in each sample we derive the 95% confidence interval, 95 of those 100 samples would include the true population mean. And imagine so there's only a 5% chance that you'd be wrong. There's only a 5% chance of not including the true population mean. So if you were to, on the first try, your odds ratio includes, your confidence interval includes the population mean, that's not good. So we consider that not being significant. So the population mean for the population mean for the null hypothesis. The null hypothesis is that there's no relation between between exposure and outcome. So in that case, our odds ratio would equal 1, right? If there's no relation. So if our confidence interval includes 1, we'd say, that's not significant. All right, so let's go ahead and make this calculation here. So unfortunately, due to my lack of a tool that allows me to write at this point, I'm going to show you what I did in this calculation based on a picture, but I'm going to go over everything very carefully for you. And we're going to use an example one of my favorite examples from a textbook that I use in teaching stats. The question is, can animals be trained to line dance? This comes from Andy Field's textbook on statistics. If you're not familiar with it, you should read it. He's awesome. Participants were 200 cats, and we want to know if they can line dance if we use different types of rewards. The cats were trained using either food or affection as reward, but not both. And let's see, so dancing was the cats either learned how to line dance or did not. So that's your outcome. So this is what we're interested in. Success would be cats learning to line dance, and failure would be learning not to line dance. The predictor variable is either food as reward or affection as a reward. So you can imagine this being an experiment where kitty cats were randomly assigned to food as a reward or affection as a reward, and we wanted to see if they could line dance. So here's the distribution after we took all the kitty cats and so after this, obviously you see the chi-square down there. We're not dealing with that right now. So could they dance? So 28 kitty cats could dance with food as reward, 10 could not. 48 could line dance with affection as reward, 114 not. And here we have all these marginal values. These are totals, like this is the total that could line dance, the total that could not line dance, the total that received food as reward, and the total that received affection as reward. So that's the key here. Okay, so you want to maybe take a picture of this, or save it so you can actually know what I'm talking about. And I'll go back and forth, I guess. All right, so let's go to my picture here, and let's see if I can enlarge this sucker a little bit. There, ooh, that's too large, huh? There you go. Let's start with the odds ratio here. This is actually pretty nice. It's maybe a tiny bit. Okay, this is pretty nice. Okay, so let's calculate the odds here. So we said 28 kitties line danced, right? And 38 did not line dance. So let's go back here. So 28 line danced out of 38, right? 28 out of 38 could line dance for food as reward. So our exposure here is having food as reward, and our outcome is yes or no. So we're going in this column. We're going this vertical direction here, right? Okay, so let's go back to here, and in this case, I'm showing you what the odds of line dancing are. So I'm just calculating the odds at this point. 28 over 38 divided by 10 out of 38. So 28 of 38 could line dance, given food as reward, and 10 out of 38 could not line dance. So this is success. This is the probability of success divided by the probability of failure. And when we do that, if we take this denominator and bring it up to the numerator, we take the inverse of this, so it becomes 38 times over 10, right? And you'll notice that the 38s cancel out, and what we have is 28 divided by 10, which is 2.8. And let's go back to that picture for a second here. And when I was talking about odds ratios, I mentioned that we don't need to divide by the total. We can just take 28 divided by 10. And basically this is showing you why we could do that, because the denominators cancel out. So let's see what the odds of dancing for affection are. Odds of dancing for affection, we do the same thing, and we get basically 48 divided by 114, which is 0.42. So 48 divided by 114, okay? So now that we have those two, we can actually calculate the odds ratio. So the odds of dancing for food divided by the odds of dancing for reward is 6.667. It's really, really important to know how to interpret this. So the odds of a cat, well, cats are, I'd say it this way. Cats are 6.667 times more likely to dance for food than to dance for reward. Or you could actually say it in something, a little bit more simple. You always have to provide the actual values, but you can say something like cats are over 6.5 times or 6.5-fold more likely to dance for food than to dance for reward. Okay, so now we have to calculate the confidence interval. By the way, if you wanted to know what the odds are for cats dancing for affection as reward versus dancing for food as reward, all you'd have to do is divide this value into 1. So you'd go 1 divided by 6.667, that equals 0.1499 or 0.15, right? Then I could say cats are, I take 1 minus 0.15, cats are 85% less likely to dance for affection as reward versus food as reward. So I could do that as well. Sometimes you need to do that when you're doing a calculation. All right, now let's go ahead and calculate the 95% confidence interval. So what I did here was let me pause. I want to show you something because I'm just like a nut about making sure that you guys know everything. I don't want to leave anything left blank. So I pulled up a z-distribution table just to make sure you understand why we do what we did. Earlier, when I showed you the formula for the confidence interval, I noted it was, there was a z1 minus alpha divided by 2 times the standard error for the margin of error. So I said z, we're using the z distribution because like a lot of things follow on standard normal distribution. A lot of the sampling distributions of values when you have a large enough sample follows a sampling distribution, a standard normal sampling distribution. So we can go ahead and use this z here. Z, pure alpha, we set at 0.05. 0.05 alpha is associated with 95% confidence. Confidence is the opposite of a probability of a false positive result. So we have 1 minus alpha divided by 2, because again, our normal distribution is symmetrical. What happens on the right side or above the I call it the expected value, just rather than the mean. I feel more comfortable with that. Is symmetric. It happens at the bottom end. So they're symmetrical. So whatever you see above the mean is the same as you see below the mean. So here we divide it by 2. So if we divide alpha divided by 2, 0.05 divided by 2 is 0.025. 1 minus 0.025 is 0.975. So we go to our table here. We look for a z value, and this is looking at a two-tail test. Let's see. Points. Well, in this case, because we're trying to find the critical value, what any of these z tables, what's in the meat here, in the body of the table, is the percentage going from left to right. So this is like what we call a cumulative distribution function going from left to right. All functions of probability, and we call it, again, I'm not going to cover this thoroughly right now, but all of these functions are called probability density functions, and they must, at least with quantitative variables, they must sum up to the value of 1. So everything goes from left to right is going to go from 0, negative infinity to infinity. Positive infinity is going to go from 0 to 1. So we're looking for something that equals 0.975, right? Because that's what we calculated. 1 minus alpha divided by 2 was 0.975. So we're looking here for 0.975. Oh, look, here it is. So you got to look for that value. And then we look for the z value that's associated with this. So this is 1.9, and we go to 0.975 here, and that is 6. So it's 1.96. So if we go back to this picture I have, you'll see that I put a 1.96 in here, 1.96 for the z value. Okay, so that's how we do that. So again, it's plus or minus because this table is symmetrical. Whatever happens on the right side of the distribution also happens on the left side of the distribution. You should Google a normal distribution to take a look if you don't know what that's about. But I talk about that in a different video somewhere else. And so our standard error, we just simply divide 1 by each of these values, right, from each of the cell values, and take its square root, and we get 0.1653195, square of that, and we get 0.406595. I use a lot of values here to make it more accurate. You don't have to obviously use so many values. So our margin of error is 1.96 times that standard error. We get 0.7969. Okay, now, as I said, this is in a natural log scale. So we calculated the odds. The odds are not in a natural log scale, right? So what we need is the log of the odds. So the natural log of the odds is 1.897. So now that I have that, I can plug this into the formula here. So eventually we want to bring it back to the odds ratio scale. So that's why we exponentiate here, right? So it's going to be e raised to 1.897 plus or minus our standard error. Plus or minus our margin of error, right? We get these two values, e raised to this log odds and e raised to that log odds. We exponentiate and we get 3.00498 and 14.789. So now we can finally complete our task and say our odds ratio is the odds of cats dancing for food versus dancing for affection as reward is 6.667, and the 95% confidence interval is 3.00498, 14.789. As we can see, this does not include 1. So it doesn't cross 1. It doesn't cross 1, so we know that this is a significant effect. So there's a significant effect of the type of reward on whether or not a cat line dances. And if you can envision a cat line dancing, that'd be really cute. Notice here, if you were to just use the log odd scale, this is also, you can tell it's significant because it doesn't cross 0 in that case, right? Because e to the 0 is the same as 1. So either way, you can tell. All right, so basically the cats are over 6.5 times more likely to line dance for food as reward than for affection as reward, and the 95% confidence interval is basically 3 to 14.789. All right, that's that. That's a wrap for this part. Next part is coming up soon.